All right, everybody. In this video, we're just picking up right where we left off in the previous video about Chapter 6. I hope that last video and all of the material is still fresh in your mind about discrete random variables. Now we're getting ready to talk about the binomial distribution. First, let's introduce another motivating example. So suppose you are a quantum physicist and you're executing a quantum physics experiment in which you expect a 25% probability of detecting a photon, at some photon detector during each trial of the experiment. And in the experiment, we're going to have 20 trials. So it means 20 trials per experiment. Out of these 20 trials, what's the probability of detecting a photon 0 times? Well, if the probability that we detect a photon is 0.25, that means that the probability of not detecting the photon, that's 0.75. That's just the complement rule from Chapter 5. So if we're asking about the probability of detecting a photon 0 times out of 20, that means we have to land on the not detect outcome 20 times in a row. And since those are all independent trials, so they're all independent events, I can use that multiplication rule from Chapter 5 to multiply 0.75 times itself 20 times for the 20 trials. And so that would be like 0.75 to the power 20. And this is a very small number, I think. We might as well put it in the calculator. So 0.75 to the power 20. All right, so that's about 0.317%. It's a very small number. What about the probability of detecting a photon 20 times? Well, the probability that we detect is 0.25, and for this to work, I need to detect this photon all 20 out of 20 times. So that would be 0.25 to the power 20, and this is going to be an even smaller number because I'm multiplying 0.25 times itself 20 times, and of course this number is super tiny. Okay, what about the probability of detecting a photon exactly 7 times? Well, if you remember from the previous video, this sort of question, when it's not 0 times and it's not the maximum number of times, this kind of question is going to require us to first, calculate what would be the probability of getting the first 7 as a detection and the last 13 as a not detection, and then we're going to have to multiply by the binomial coefficient, where we have 20 choose 7. Because there's 20 trials, and we have to choose among those 20 trials which 7 are going to have a success, or which 7 are going to detect a photon, right? And this 20 choose 7 is not super easy to calculate. That would be like 20 factorial divided by 7 factorial times 20 minus 7 factorial. And the factorial is not super easy to calculate on its own. And so this is going to actually require, probably a calculator and definitely a little bit of time. Rather than do that, though, let's just keep that thought in our mind about why we might want to calculate the probability of detecting 7 times. And we'll notice that the number of times a photon was detected, that is also a discrete random variable. It's discrete because you can't detect a non-integer number of photons, right? We can't detect 2.5 photons. And it's random because it comes from a random process. And this is kind of the nature of quantum mechanics, where you can make probabilistic statements about particular outcomes, but we can't always, predict something because it's not strictly deterministic. Now, here's some vocabulary that we're going to be using a whole lot. The phrase Bernoulli trial is important. A Bernoulli trial is a trial that results in either a success or a failure. Basically, a Bernoulli trial is a trial that has two outcomes, or two possible outcomes. So in our previous video, we used the example of bowling, where you stepped up to bowl and you were either going to roll a strike or you're going to bowl something that was not a strike, right? And so we might say that a strike is a success, but failing to bowl a strike would be like a failure. And if you look at it through this lens, each time you step up to bowl is like a Bernoulli trial because there's two possible outcomes. In our new example, our physics experiment is also a Bernoulli trial because we could say that detecting a photon is a success and failing to detect a photon would be a failure. So looking at it through this lens, each one of these trials is a Bernoulli trial because it could only be one of two possible outcomes. Now, again, talking about new vocabulary terms we need to know, make sure you're familiar with the binomial distribution and what it means to be a binomially distributed variable. In both of those two examples, bowling and quantum physics, our discrete random variable was the sum of the number of successes in several Bernoulli trials. So we set up an experiment. The experiment consisted of multiple Bernoulli trials, and our discrete random variable was just adding up the number of successes out of those trials. So when this is the case, we say that our random variable is binomially distributed, or we could say that our random variable follows a binomial distribution, and these mean the same thing. It's different ways of saying the same thing. Now I know Bernoulli and binomial both start with a B, and the ideas are associated with each other in this way, but make sure you keep it straight in your head, sort of the difference here. Now, a lot of this is just learning new terms in this lesson, but if we have a binomially distributed random variable, the probability of any specific outcome, that is a number of successes, is going to be described by what we call the probability mass function, and you'll see it abbreviated PMF for probability mass function. Now, what this is saying is that when I ask you the question, what's the probability of detecting a photon 7 times out of 20, like we did before in that example, what we're asking is, what's the probability that this discrete random variable, that is the number of times we detect a photon, is equal to 7? And what I'm telling you right here is that this is the same thing as the probability mass function of the binomial distribution when I evaluate it at the number 7 as an input. And maybe you shouldn't be super surprised to see the second line of math here, where you see the n choose k, the binomial coefficient here. What that's saying, n is the number of trials that we're going to run, and k is the number of successes we're looking for. So we're talking about 20 choose 7. That coefficient there is saying that we need to multiply my probability times the number of different ways I can choose 7 out of the 20 Bernoulli trials to be a success. And so hopefully that's, really clicking now at this point. We don't actually have to worry too much about this mathematical form. Don't feel like you have to memorize that, because our calculator, TI-84, is going to be able to do that for us. And I put a little note down here in the bottom right hand of the slide, because whenever we're talking about the binomial distribution, this function is called the probability mass function. But for whatever reason, the engineers at Texas Instruments put in, I guess, a little bit of a typo, and they called it the PDF in their calculator. And so you can see my face down here is, I'm rolling my eyes because it's just a little bit frustrating that they called the probability mass function the PDF. Again, this is the mathematical formula for the PMF, and this again is the binomial coefficient here. And n is the total number of Bernoulli trials. So like when we were bowling, we had 3 Bernoulli trials per experiment. And in our quantum physics experiment, we're talking about 20 trials per experiment. P is the probability of success for any one Bernoulli trial. So when we were bowling, P was 0.6. But for our little example with the quantum physics experiment, P would have been 0.25. And K is the specific number of successes that you're looking for. Okay, so the way this works on your TI-84 calculator, this is probably the most important thing for you to remember for an exam, is we're going to click second and then DISTR for distribution. That goes right above the variable or the button VARS. So we click there. We're going to have to scroll way down to the bottom, past the number 9, past the number 0 to A. And again, notice it says BINOM for binomial, and it says PDF, but that actually, remember that's probability mass function, that's just a typo. But anyways, we go down to A, and we click A, and the first thing it asks me for is how many trials do we have? And remember from our example, we had 20 Bernoulli trials per experiment. The probability of detecting a photon was 0.25 in any one of the Bernoulli trials. And then for x value, we were asking the question, what's the probability that we detect exactly 7 photons among those 20 experiments? So then we click paste, hit enter again, and we find that that probability is 0.112. Okay, so that's how you do it on the TI-84. You can also do this in Excel, and in an Excel spreadsheet, click on any cell and type in equals binom.dist, open parentheses. We'll put in 7, because that's the number we care about. The total number of Bernoulli trials, I'll type in comma 20, and then comma, the probability of success for any one of the Bernoulli trials, like 0.25. And then comma, we're going to type in false. And notice that Excel knows that this is actually called the probability mass function. And that text might be a little bit small in the video, but of course, hopefully you're trying this, in Microsoft Excel as you watch the video, and so you can see what I'm talking about. Close parentheses and type enter, and we find the probability of 0.112, just like in your calculator. Okay, here's a new concept. For a binomially distributed random variable, the probability of any outcome less than or equal to a specific outcome, that's going to be described by what we call the cumulative distribution function, or the CDF as an acronym abbreviation. Now, the CDF of the cumulative distribution function is basically just adding up the little probabilities for all of those values of the probability mass function up to the point K that you get to specify. So again, this is where the less than or equal to comes in. And on your calculator, here's how you find it. So on your TI-84, we go to second DISTR, and then we find B, which again we scroll way down to find BINOM CDF. Select that, and again it's asking me for the total number of Bernoulli trials, P, the probability of success for any one Bernoulli trial, and then the X value that we actually care about. And so to give it a good example for this, let's scroll way back to the example that we showed in the previous video to this, so we're going to go back to our bowling example, on this very, very messy slide over here on the right, we calculated cumulative probabilities in the process of finding the median of this distribution for this discrete random variable. So I'll go ahead and circle this in a different color, maybe this nice pastel blue over here. And so if I were to, do what we're talking about, which is add up the probabilities for everything less than or equal to the probability 2, the probability of bowling 2 strikes, I should get 0.784. That's at least what we calculated in the last video by hand. So in our bowling example, we were going to bowl 3 times. We said that the probability of bowling a strike was 0.6. And like I said, let's talk or ask the question, what's the probability of bowling 2 or fewer strikes given 3 opportunities? So we'll type in 2 for my x value. So we go down to paste and hit enter. We find that the probability here is 0.784. And that's what the cumulative distribution function does, is it'll just give you these values for the cumulative probabilities. So you could read this as saying, well, the probability of bowling 3 or fewer strikes given 3 opportunities is 1, so that's a guarantee, right? The probability of bowling 2 or fewer strikes is 0.784. The probability of bowling 1 or fewer strikes is 0.352. And then the probability of bowling 0 or fewer strikes given 3 opportunities is 0.064. So again, using that example from last video and showing you what happens when we use that binomial CDF, the cumulative distribution function of our binomial distribution. You can also do this in Excel, and it's the same formula as before, but we just type in the word true at the end. So we can get the same result if I say I'm interested in 2 successes from 3 Bernoulli trials with a probability of 0.6. But I want the cumulative distribution function, so I type in true. At the end, you can see Microsoft Excel also tells us that is 0.784. Now, whenever you are talking about a binomial random variable, the measures of central tendency are actually easy to calculate. Like the population mean is just n times p, where n is the total number of Bernoulli trials, and p is the probability of success for any one of those Bernoulli trials. So let's go back to our example from last video. We calculated the mean for our bowling example distribution, and that was 1.8, but it took us a little bit of effort. When we consider that in the number of strikes we bowl given 3 opportunities, since that's a binomial random variable, let's try our formula. So n is the number of trials, that's 3, times p, which is the probability of success, that's 0.6. And my calculator tells me that 3 times 0.6 is 1.8, which is just like what we calculated before. So that checks out, doesn't it? And that's a whole lot easier than doing what we did in the last video. So very nice shortcut here. For the population mode, we multiply n plus 1 times p, but then we round down. So n plus 1, that would be 3 plus 1, which is 4, times p is 0.6. That gives me 2.4, and then of course I round down from 2.4 gives me 2. That should be my population mode. And let's see if that checks out. Is my population mode 2? And yeah, like we found in the last video, the population mode for this example is 2. There's not necessarily a shortcut for finding the median, but we can also have a shortcut for measures of dispersion. Like the population variance is going to follow this formula, n times p times 1 minus p, so very important to know. And then this, remember, the standard deviation is always just the square root of the variance. So if I use n times p times 1 minus p on our previous example, that will be 3 times 0.6 times 1 minus p, that'll be 0.4. That gives me a variance of 0.72, and then just to show you that previous slide again, we did find that the variance was 0.72, and then of course to calculate the standard deviation you just take the square root of the variance, which we did before as well. So these are awesome shortcuts that you should know to use for a binomial random variable, and you'll also find these on your formula chart. So you don't necessarily have to memorize them for the exam, you will be able to find them on your formula chart as well. So one more example, and then we will take another break from this video. Let's read this example problem. Now suppose you expect your favorite NBA player to make each of his free throws with a 70% probability. So you watch him shoot 20 free throws, and then we're asking a bunch of probability questions down here. But first, let's point out that the 70% probability is going to represent a lowercase p value of 0.7. When we watch him shoot 20 free throws, well, you can think of each of those free throws as a Bernoulli trial, because each of those free throws can have one of two outcomes. Either you make the free throw or you miss the free throw. So this is 20 Bernoulli trials in this particular experiment. So when we ask what is the probability of him making 0 baskets, this is actually evaluating the probability mass function of the binomial distribution at 0. And that's because, whenever we're adding up the number of successes in 20 Bernoulli trials, that's a discrete random variable that is binomially distributed. The number of successes, if it's the sum of the number of successes from 20 Bernoulli trials, that is a binomial random variable. So anyways, when we ask the probability of him making 0 baskets, that's going to be the PMF evaluated at 0. Likewise, 20 baskets, that just means we evaluate the PMF at 20. And what's the probability of him making exactly 15 baskets? Well, that would be the PMF evaluated at 15. What's the probability of him making no more than 15 baskets? No more than 15. So another way you could say this is you could say, what's the probability that he makes less than or equal to 15? And if I'm asking what's the probability that he makes less than or equal to 15 baskets, that's actually the cumulative distribution function of the binomial distribution evaluated at 15. No more than 5 baskets is asking what's the probability that he makes less than or equal to 5 baskets, which is, again, the cumulative distribution function evaluated at 5. And when we say what's the probability he makes more than 17 baskets, this is important. So pay attention here. The probability he makes more than 17 baskets, that's going to be 1 minus the probability that he makes less than or equal to 17 baskets. But this follows from the complement rule, by the way. So think back to chapter 5 when we talked about the complement rule. What I'm trying to tell you is that if you shoot 20 free throws, this can only happen one of two ways. Either you make more than 17 baskets, or you make less than or equal to 17 baskets. So that means when I add the probability of making more than 17 plus the probability of making less than or equal to 17 baskets, those two probabilities have to equal 1. This is what we mean by the complement rule. And so then this becomes 1 minus the cumulative distribution function evaluated at 17. Cool. So every one of these probability questions can be evaluated in terms of either the PMF or the CDF of the binomial distribution. And that's a handy thing to know because your calculator can do those problems really, really quickly, really easily. And so let's actually use our calculator to evaluate. What's the PMF at 0 for this problem? So I go second distr, and then I'm going to choose A for the binomial PMF. Remember, we all roll our eyes when we get to binom PDF in the calculator, because it should really be the probability mass function. Now, the number of trials, the number of Bernoulli trials, is 20 free throws total. The probability of making it is 0.7. The x value that we're interested in here is 0 baskets, and so we can do that. And that's a really, really tiny number. That's 3.49 times 10 to the power negative 11. So imagine 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 3, 4, 9. That's the answer here. Okay, what's the probability mass function evaluated at 20? So same thing in my calculator, except I'm going to replace the x value with 20 instead of 0. And this probability is also very small, but a little bit larger than before, 7.98 times 10 to the negative 4 power. So that's like 0.000798. What about the PMF evaluated at 15? And I change my x value to 15 now, and paste, and this is 0.179. So there's actually like an 18% chance that he's going to make exactly 15 baskets. It's pretty good. Okay, switching colors. What if I evaluate the CDF at 15? So this time I go second distr, and then I choose the binomial CDF. The number of trials is 20, p is 0.7, and the x value I care about now is 15. So now it's 0.762. If I evaluate the PMF, or sorry, if I evaluate the CDF at 5, let's try that. That's going to be a really small number, 4.29 times 10 to the negative 5, which is 0.000429, pretty small number. And then what about the probability of making more than 17 baskets? Well, I'm going to write 1 minus the CDF evaluated at 17, and so this is going to be 1 minus, and I get to the CDF, it's B on our list. I want to evaluate this at 17. And so 1 minus all of that is going to be 0.0355. So like 3.5% chance that he makes more than 17 baskets. Okay, so let me just read that out loud. What's the probability of him making 0 baskets? A really tiny number. What's the probability of him making exactly 20 baskets? Also a really small number. What's the probability of him making 15 baskets? 18%, pretty good chance. What's the probability of him making 15 or fewer baskets? Well, that's like 76% chance that he makes 15 or fewer. What's the probability that he makes 5 or fewer baskets? That's actually a really, really small chance. What's the probability that he makes more than 17 baskets? That is the probability he makes 18 or 19 or 20 baskets. That's about 3.5% chance. Okay. Cool, cool. Let's see what we have on the next slide. Suppose you expect your favorite NBA player to make each of his free throws with 70% probability. So same problem as before. We watch him shoot 20 free throws. This time we want to calculate the mean, median, mode, variance, and standard deviation. Well, this time let's use our little shortcuts, right? So our shortcut for the mean is going to be doing this. We say that the mean is going to be n times p. N is 20 and p is 0.7. So this is going to be 14. Man, that was so much faster than what we did in the last video, isn't it? What about the mode? So the mode is going to be n plus 1 times p, and then we round down. So that's going to be 21 times 0.7, rounded down. So 21 times 0.7 is 14.7, round down, and it's 14 again. For the mode, what about the variance? So the variance is going to be n times p times 1 minus p. And so that's going to be 20 times 0.7 times 1 minus 0.7 would be 0.3. So let's do 20 times 0.7 times 0.3. That's 4.2 for the variance. So variance, sigma squared, is going to be 4.2. And then of course standard deviation is just the square root of the variance. So it's the square root of 4.2. So just take that previous answer and then raise it to the 1/2 power. And then the standard deviation is 2.05. Cool. So that's how you calculate these descriptive statistics. Maybe you notice I skipped over the median. And the median is going to be a little bit harder to calculate. So the median is, again, that number for which the cumulative distribution function goes from less than half to more than half. That's the definition of the median we gave in the last video. So, you know, the CDF evaluated at 5 is way less than half. The CDF at 15 is a little bit more than half. Let's try the CDF at 14 and see what happens. So I do the binomial CDF, and now we're going to try 14 to see if maybe that is less than half. And it's not. It's still a little bit more than half. So let's do this again. Evaluate the CDF now at 13 and see what we get, hoping to get a little bit less than half. Wow, okay, it is less than half. So going from 13 to 14 makes the cumulative distribution function jump from like 0.39 up to 0.58. So actually the median here is going to be 14. That's what puts us over the halfway point. So this median is going to be 14. And maybe you could have guessed that based on the mean and the mode. Right? The median is always in between the mean and the mode anyways. Okay, now suppose you expect your favorite NBA player. Oh, this is the same question. I just left myself more space to do the work. Oh well. Now this is going to be the end of this video, and we're going to work on one final skill in the next video for chapter 6.